So in our next point, we're going to be comparing the gravitational electric field strengths at a given distance from a mass or point charge using the equations. So it's not necessarily a comparison, but we are going to be showing the relationship. Now we know that the strength of the gravitational field is going to be the force divided by the mass that it's acting on. So instead of having two masses up here, we just have the mass of the field's source. Similarly, the strength of the electric field is given by K and then a single charge, just the one at the source, over R squared. So these are the magnitudes of the forces. Now we will be very careful anytime we refer to the electric field strength to use the absolute value of the vector. Otherwise, the notation is really difficult to distinguish between electric field strength and energy. So always watch for that vector arrow with the absolute value bars. That's a dead giveaway that it's electric field strength and not an energy, because energy is a scalar and not a vector. So these are the equations that were being used. Now in both cases, you have a 1 over r squared dependence. So if you have the strength of the field, and I'm just going to use S because it doesn't really matter which field it is, and plot it against the radius r, you're going to get this exponential decay. It's going to taper off and come closer and closer and closer to the x-axis without ever actually touching the x-axis. It should actually be a smoother curve than what I've got drawn here. It should be more like this. The reason we have that 1 over r squared dependence comes down to the existence of field. That 1 over r squared dependence is called the inverse square law. But imagine that you have a field source, and these field lines are coming out in all directions. Now there's no actual field lines, and in reality there's infinitely many because every part of space is filled with them. But by convention, we choose to draw lines, and the more dense the lines are, the stronger the field. But let's say you are a distance r away. Well, the strength of that field that you exhibit uses what they call the cross-section, your charge, your mass, but it's almost like you have a certain amount of area here. And the strength of that pull, the strength of this field or the force, depends on how many field lines intersect this area. Well, to figure out what that number is, we could do proportions. So the force is going to be proportional to, that's what this shortened alpha is. It's going to be proportional to the number of field lines being emitted times the area of your shape. These are both constants at all points in the field, divided by the area of a sphere of distance r. Because then your area divided by the area of that sphere tells you what proportion of these field lines are going to be going through that space. Well, the area of a sphere is 4 pi r squared. And in fact, that K Coulomb's constant that we see in the electric force equation is now known from theory to be 1 over 4 pi epsilon naught. Coulomb found K in the lab. He just knew it fit. But this 1 over 4 pi epsilon naught comes from theory, where epsilon naught is called the electrical permittivity of free space. It's a measure of how easily an electric field can penetrate the material you're in. But this is where that 1 over r squared comes from. You can drop the n and the a because those are just proportionality constants. You see we have the 4 pi, which goes directly into our k, and here is our r squared. That's the inverse square law. So this is how the inverse square laws come about, and that's the main defining feature of these forces.